Good evening, everyone, and welcome to SocialFlight Live. I'm Jeff Simon. We have an out-of-this-world show for you this evening. Yes, I did say that. Håvard Grip is here, Chief Pilot of NASA's Jet Propulsion Laboratory Mars Helicopter Ingenuity program. And we're going to talk about his background, what brought him to JPL and NASA. We're going to go inside that amazing organization, learn about what made it possible to fly a helicopter on Mars and get that real story that goes behind all that. And perhaps, if there's time, we're also going to be able to talk about what is coming next when it comes to Mars exploration and aviation. Before we get started, just a couple fun things as we fly into fall here at SocialFlight. We have tens of thousands of aviation events and destinations, all sorts of amazing, cool things from leaf peeping to cider and other cool places to go and things to do for fall. Be sure to check it all out at socialflight.com and the free mobile apps for Apple and Android devices. It's one word, just SocialFlight. Check that out and you'll be able to join in so many things that we do, including our FAA Learning Center, where we have so many programs that you can take courses, get wings credit if you are a mechanic, especially one that wants to participate in the Aviation Maintenance Technician Awards program, or if you are an inspector, an IA, and you want to get your continuing education for your IA renewal. It is all available and free at socialflight.com. Just go to the FAA credits section of that. And lastly, we have our Fly to Win challenge. We are giving away a Lightspeed Delta Zulu headset on October 1st. All you need to do is get the mobile app, check in, and you're entered in to win. Go fly around, get a bunch of points, and compete on our leaderboard. You get an extra entry and win as well. But check all that out. We have so many cool things going on there. Tonight's broadcast is brought to you by Michelin Aviation Tires and their amazing new Pilot tires that I personally trust with every landing in the Bonanza. I'll tell you, recently I switched over to these tires and I can actually feel a difference. It's remarkable. There's a lot of new technology in it. They last longer than I've ever seen and handle better than any tire I've ever put on the aircraft. And so be sure to check it out for yourself. It really helps a lot. And since we were talking before about giving stuff away, we actually gave away a complete set of Michelin Pilot tires at AirVenture when we were there as part of our Snag Some Swag contest. So again, thank you so much to everyone who keeps the lights on here and makes SocialFlight possible. Now to tonight's show. Håvard Grip is a Norwegian cybernetics engineer and robotics technologist. He was the chief pilot of NASA's Jet Propulsion Laboratory's Mars Helicopter Ingenuity program and led the development of its aerodynamics and flight control system. He successfully flew Ingenuity's first flight on Mars on April 19, 2021, which made history as the first extraterrestrial helicopter flight. He's currently manager and chief engineer of future NASA and JPL Mars helicopter programs. So buckle up for launch. We are going to take aviation beyond Earth's orbit and to the red planet. You're going to learn a ton. Please welcome to SocialFlight Live, Håvard Grip. How are you, sir?
Very well, thank you.
Hey, thank you so much for taking time out of your day to join us here on the show. I know how busy you are in obviously everything you've done up until this point, and you have your plate full in figuring out what's next for Mars. So I just want to say thank you, first of all, for taking time to join us.
Thank you so much for having me.
So I'd like to go back in time a little bit and understand, there's a lot of people out there, either themselves interested in what it takes to wind up in shoes similar to yours, working in a place with that kind of backdrop that's behind you right now, and even kids looking at what kind of career path takes them to NASA and to JPL. So tell me your story.
Well, I think part of why I've ended up where I am now has a lot to do with just my interests outside of work. I like computers, I like math, I like physics, I like things that move. I've flown airplanes, I've experimented with cars previously in my career, and flying a helicopter on Mars is kind of the perfect combination of all of those interests.
So, did you? I mean, tell me a little bit about the path. Like, what did you do as far as university, and then and kind of a job path?
So my background is in something called engineering cybernetics, which we more typically call control engineering. And what it is has to do with taking physical systems, which could be a car or a helicopter or an airplane or a chemical plant for that matter, any kind of physical system, you're trying to get it to behave in a certain manner by controlling it. That's what control engineering is all about. So you take sensor data, you do certain computations, you design the algorithms that do those computations, and then you use actuators to make it behave the way you want. So that's my technical background. So I have a master's and a PhD in that, and of course that's a great preparation for this kind of work. And then I have a personal interest in aviation as well, which meshes really well with this particular application.
Did you always have kind of a fascination in the mechanical side of things? I've found that that people who were extremely talented in the kind of the technology and the coding side of things, but really wanted to see it move something in real life, that's sort of built into your soul a little bit.
Yeah, I'm not going to pretend that I'm not a mechanical engineer. There are other people who know that part of it, but I do enjoy that practical side of it. It's great to do theoretical work. It's great to do paper studies, but at the end, it's when you get to building hardware, that's when the rubber meets the road. That's when things really happen. So that's really, the most fun for me is to see it actually take shape in real life.
Yeah. Well, you came from Norway, so what brought you to the United States and then eventually landing at NASA and JPL?
Combination of things. I'm married to an American, and so that's certainly part of it. And then the opportunities that I've had here at JPL is not something that you can find anywhere else. There's nowhere else you could go to do this kind of work, and so that's very attractive from my perspective.
Yeah. Well, let's talk about the program a little bit. Tell me how when you came on board, and a little bit about the history of the Mars mission that involved Perseverance and also Ingenuity. And I'm going to bring up an image here that I think is quite telling of these different vehicles.
Yeah, so exploration on Mars has a long history now, starting with orbiters and then landers, and then at a certain point, somebody had an idea of putting something that could move on the surface, right, a rover. And so that little rover that you see in the foreground there was an experiment, a technology demonstration to show that you could build a wheeled vehicle that could drive around on Mars. And that really gave rise to subsequent missions that really made use of that mobility. So you see Mars exploration rovers. There were a couple, were two of those. That's an example of that to my right there. And then later, we've had two large-scale rovers, Curiosity and Perseverance, that are, much larger, as you can see. And the helicopter that we're talking about here, Ingenuity, we built that as a technology demonstration that went along with the Perseverance rover. So in a sense, it followed the footsteps of that little rover first, which sort of blazed the trail for exploring Mars using wheeled mobility. In a similar manner, Ingenuity, the purpose of sending it was to do that same thing for aerial mobility, to show that it's possible, so that this, to establish it as a technology that we can now leverage for real for Martian exploration.
And those first ones that's standing in front of you and to the right, that was basically a model of Opportunity based. Is that accurate?
So yeah, Spirit and Opportunity are the Mars exploration rovers that went and landed on opposite sides of the planet. And so what you're seeing to my right there is a model of one of those two rovers.
Got it. So So tell me about when did you come onto the program, and let's talk a little bit about the how the Perseverance program went, and how that experiment of putting Ingenuity on board happened.
Well, it goes back to some of the work that was being done here at JPL back, a little over a decade ago on Earth drones. So there was a lot of work being done here, especially in a particular lab where we're doing things like autonomy for drones here on Earth. And in fact, our lab director visited that lab and thought, well, could we do this on Mars? We're JPL. We like to send things to Mars. Could we do this on Mars? And at the time, our chief engineer, Bob Ballaram, actually had kind of an answer to that, because back in the 90s, he had done some preliminary experiments with a rotor in a chamber here at JPL, where he replicated the Martian atmosphere. And it was a very simple thing. It was this very simple rotor that just, teeter-tottered on, a little pivot, and then it lifted off, and you could see that it was generating thrust. But that was sort of a good enough starting point to say, yeah, that's possibly something we could do. And so we got the investment at that point, the support of the institution, to go after that idea and try to develop it into something real. And so we started in earnest in 2013 on that. And along the road to development, we have built a couple of different prototypes that gradually showed that this was possible, and also taught us a bunch of lessons along the way. And then we finally, earned our place on the mission as it, was getting closer to launch in 2020.
Is that how it works? That you work on a concept, you try to essentially prove what you can do, and as you mentioned, you earn your place on board?
It varies. There are different types of missions, and so this has its own history, Ingenuity, that isn't necessarily the same as other missions. But that was, in a sense, how Ingenuity came about. We had a lot to prove before it was really possible to baseline it as part of this larger mission.
Can you give me a sense why a helicopter? I mean, in Earth terms, helicopters are generally more complicated than any type of fixed wing vehicle, and at least throughout history they have been. So why was your first shot like, we're going to do a helicopter?
So they are definitely complicated, and they don't get any easier on Mars. But they do have certain properties that are good for what we try to do. Like, one thing is, you don't have any runways on Mars, so that's, let's just start there. That's an obstacle to doing fixed wing. And you have to go really fast too, right? So you have a density that is ridiculously low compared to Earth. It's about 1% of the atmosphere that you have at sea level on Earth. So that means you have to go fast. And so you can imagine, the difficulties that arise if you were to try to design a fixed wing platform were to take off and land on the Martian surface without any runways. So a helicopter obviously is beneficial in that sense, with being able to do vertical takeoffs and landings.
That makes perfect sense. So then take us through the Ingenuity helicopter, because this is a kind of a little map of or description of all the different components that make it up. Yeah. So let's start on top. So it's hard to see in this image, but there's a small antenna there, which we use to communicate to the rover, like to the Perseverance rover. We couldn't communicate directly to Earth or directly to orbit, so we had to stay within a reasonable distance of the rover and communicate with a similar antenna, through a similar system on that side. And then below that, you see the solar panel. So that was tuned to it was especially manufactured for this mission and tuned to the Martian solar spectrum to get as much energy as we could out of that solar panel area.
And below that, you see the rotors. So the rotors are maybe sort of the biggest miracle here. A lot of work went into defining what those rotors needed to look like, both in terms of shape and also in terms of structural properties. So these are made out of carbon fiber around a foam core, very lightweight, very stiff. Those are both key things for being able to control the helicopter in this thin Martian atmosphere. Below that, you have the body of the helicopter, or the fuselage. This is, looks bigger than what's inside of it, because there's a CO2 gas gap insulation, in order to help it keep warm. And then there's internal heaters inside there as well to try to keep warm, especially throughout the Martian nights, where temperatures get down to about minus 90 degrees C. So very cold. And inside that, you find all of the sensitive electronics, batteries. You also find sensors, cameras, and at the bottom there is the landing gear. So the landing gear is also made out of carbon fiber, lightweight and stiff, but then we have little flexures up at the shoulders there that help give us a little bit of flexibility and also take a little bit of energy out when we land, so that we don't bounce too much.
That makes a lot of sense. I know that it seems for a lot of previous Mars missions, when they start talking about how long can something last, it's often about dust and degradation of getting energy out. What did you do, or how do you handle that that issue for the solar power cell?
Yeah, so because Ingenuity was intended as a technology demonstration, our goal was to perform at most 5 flights, and it was all going to happen within about 1 month, shortly after landing on Mars. And so that's a time of year, it's in the Martian spring, and it's at a favorable time of year in terms of dust. And so we designed the vehicle for that scenario. But you're absolutely right that there are other times of year where dust becomes a big issue, not only because it accumulates on the solar panel, but because the atmosphere gets saturated with dust. So you just get fewer rays, on your solar array. And Ingenuity, of course, it lasted much longer than envisioned. And so we eventually did get into Martian winter, where that became a problem. And so we saw that this was becoming a problem, and one day suddenly, we noticed that we couldn't talk to it when we were supposed to, and we understood quickly that what had happened is that it had literally just run out of energy during the night, and that meant that it couldn't keep itself warm. All of the electronics inside the batteries, it all froze. But it's quite remarkable. We built in the capability here that it could wake itself up again once it became power positive, and it did. Even though nothing inside had been designed to withstand these temperatures, it woke up again, was confused about the time and which year it was waking up in, but we were able to reestablish contact with it. And remarkably, that then became our sort of winter operations mode, where during the night it would shut down, freeze, and then wake up again in the morning. And this kept happening, and it just kept on working until we were out of that season, and we could go back to our normal way of operating again.
It seems to laymen, to those of us out here that follow what you do at NASA and JPL, that that's sort of the expectation always, that you guys say we built this for 7 days, and then 2 years later we're following the mission and we're heartbroken when something happens, or some other crazy thing like that. Tell me about that, kind of how that happens.
Well, I think part of the reason for that is you have to think about all eventualities and all the things that a place like Mars can throw at you. So you have to build in margins in a lot of different places. And statistically, only a few of those things, or maybe none of those things, actually happen. And so depending on what in the end Mars does throw at you, you might end up having some margin left over. And I think that's when that comes into play, is in when it turns out we have greater capability than we had designed for, with appropriate levels of conservatism and greater longevity. So that's certainly the case with Ingenuity. Is there were a lot of things we didn't know, a lot of places where we had to anticipate that things could be worse than what they turned out to be in reality, and then you reap the benefits of that in just capability when you get there.
Is there a certain amount of kind of new normal that's how you guys internally end up realizing that programs can go on a lot longer than is planned?
Well, there's always a possibility of things going beyond the planned mission timeline, but really it was not really part of our thinking when it came to Ingenuity. In our minds, it was 5 flights and it was going to be over. It was really not. It was a big surprise to all of us on the team when we suddenly got the go ahead to continue the mission. And I think it really just happened when people saw Ingenuity flying and realized this is not just a toy. It's not just a simple demonstration. It's a real machine that can do pretty incredible things. But it was a surprise when we got to that point, and a surprise not least in terms of how we were operating Ingenuity. We had not planned to go exploring Mars. We'd planned for a few short flights within a very well-defined area that we'd picked very carefully. And so then to be told, now you can go explore, there were a lot of things we had to kind of invent on the fly at that point.
I can imagine. I want to take people through the process of deploying Ingenuity, because I find that absolutely fascinating. And some of these images I had never seen before. And so if you could sort of take us through what we're looking at here. If I understand it correctly, this is looking at the bottom of Perseverance?
Yeah, so this is one of the cameras on Perseverance. It has many, but taking a picture of underneath the belly after we dropped off part of what was on the rover when we arrived, but that needed to be dropped off after we arrived. So this particular piece of hardware has nothing to do with the helicopter per se, but it had to be discarded before we could go on with deploying the helicopter. What you see there, that big bulge underneath the belly, that's going to be the next thing to go here, and it's the debris shield that shields Ingenuity. So after we had dropped this at a safe distance from where we planned to fly the helicopter, we then went on to drop that debris shield, and you see that right there, also at a safe distance. And then after this, we then drove back to the place that we had chosen for our demonstration flights. And that place was chosen very carefully. In fact, I was in charge of that selection, so I spent several weeks up front in the mission obsessing over tiny little rocks on the Martian surface within a small 10 by 10 area, measuring them, discussing the risks associated with them on landing and so on. It's a process that feels slightly absurd, but in the end we found that magic spot that we felt comfortable deploying the helicopter, which I think you'll see in a moment here. And we named that Wright Brothers Field, that initial airfield that we took off from. So there you see that. That's the start of the deployment of the helicopter itself. Now we position it exactly where we want it. It's a nice flat spot there.
It looks clean. I mean, for all the other rocky places, I think you picked a good spot.
It's pretty good for where we landed. We happened to land in a place that was actually quite rocky. So there are many other places on Mars that are even more benign, but this is the area where we landed in. And so I think we found a good spot in that area. Yeah. So yeah, here you see it's sort of partially deployed. There are many steps associated with deployment. They all, it kind of take a day at a time, and then you look at images, and you initiate the next step and so on. So it takes quite a while, but here we're now in a position where we're ready to drop the helicopter to the ground, and that's the final step of the deployment. Helicopter drops to the ground. and then the rover had to drive away, and it had to do that on a particular time within a certain amount of time, so that the helicopter would become power positive with sun on the solar arrays. It didn't get stuck underneath the shadow of the rover. These are the kind of coordinated things that you have to think about when you're doing things remotely on another planet.
I know that that this next image is going to show is much later, but I think it's helpful just to show it independently, so people can get an idea of what it then looked like on its own.
Yeah, there it is, and I can't tell exactly from this image when it was taken. But
So
in any case, here it is.
Sol 46. Sol 46.
Sol 46. Okay, yeah. So we're still in that area at that point, and so you can see the tracks from the rover right nearby there. But yeah, here it's sitting with its legs firmly planted on a Martian soil, and at that point, when after that first drop and the rover drove away, it woke up and it talked to us using its radio for the first time since before launch. So we were all holding our breath at that point. Is it going to wake up? And so when it talked to us, yeah, that was a big celebration.
Yeah, I mean, that's exactly what I was going to ask you. Is like, what does it feel like to sit there and know that this thing that you have seen get built, that you've worked on, and now you get an image like this, and you realize when you look up in the night sky like this, that's where it is. That's where the little baby you built is.
Yeah, it's sort of fascinating to think about that. Yeah.
Give me a sense of scale for everybody on that. What is the diameter of those blades end to end?
So about 1.2 meters. So that's about 4 feet.
That's big.
Yeah, it's big for what it is. So that whole vehicle, it weighs 1.8 kilograms. So I guess that's about 4 pounds. And so to have the rotor this size to lift that, that's necessary only because of the low density that we're dealing with on Mars. So they're basically, to generate enough thrust, it's all about having enough rotor, and then using that rotor at a speed as fast as we can get away with, more or less. The speed limit here, as on Earth, is driven by the speed of sound. A lot of Earth rotorcraft don't really have to challenge that limit, but we do. We have to get fairly close to the speed of sound in order to generate the amount of lift that we need. An interesting thing here. Yeah, go ahead.
No, go ahead.
Well, it's an interesting thing here too, is that the speed of sound on Mars is actually a little bit lower than on Earth, about 75% of the speed of sound on Earth. So that also takes a bite out of the maximum amount of thrust that we can generate with the rotor.
I was going to say, help people understand that the science behind that at a very high level. Why does the speed of sound matter to a propeller blade? I mean, we all know that when you hear an airplane take off and it's got long blades and it's spinning at a high pitch, it is loud because they're approaching that. But it obviously has to do with efficiency. So what is it that happens as you approach that?
So what happens is you get this, we call it drag divergence. So you get drag that increases very rapidly as you approach the speed of sound. And so you don't really want a helicopter where the tips on the advancing side are going, are encountering that speed, that barrier over and over again. In part because power is one of the most precious resources that we have on the helicopter. You really you can't afford to be doing that, and so it basically puts a speed limit on the rotor itself. How fast can we spin the rotor in hover? And even though it's 3/4 of Earth, well, it doesn't sound that bad, but the amount of thrust that you can produce with a rotor goes as rotor speed squared, right? So it actually amounts to about it cuts it in about half. All things being equal, that change in the speed of sound, it cuts in about half the amount of thrust that is possible to extract from a rotor this size.
And when you design for something like that, I mean, again, all I can do is bring to the table the ideas of what we do with general aviation, and you're usually looking at more blades and a less of a diameter, so that you're not approaching all of those speeds. But you guys did it with these two counter-rotating and what appear to be fairly long blades. Can you tell me a little bit about that?
Yeah, so it's generally for helicopters, in hover and edgewise flight. You want to achieve more blade area by increasing the diameter of the rotor rather than filling up more of the rotor disc with blades. That fraction of the rotor disc filled up with blades is called solidity, and you generally want to have more blade area, not by increasing solidity, but by increasing rotor radius, because it's more efficient from a power point of view. And power, as I mentioned, is a very precious resource in our case, in part because helicopters on Mars are also not efficient power-wise. To produce the same amount of thrust in that low-density atmosphere just costs more power, and so it's one of our major constraints. Now, that being said, one of the things we've discovered when it comes to scaling up these helicopters and building larger helicopters for Mars, we are constrained also by the volume of what we can pack into an aeroshell, which is what we use to punch into the Martian atmosphere. And so one of the conclusions that are more recent of the work that I'm leading here is that for future large-scale Mars helicopters, we really need to go to higher solidity designs where we're filling up more of the rotor disc with blades. And in fact, we have a test going right now here at JPL that is looking exactly at that. What is the performance of these higher solidity rotor designs for Mars?
Oh, wow. So the next generation, which we'll talk about a little later in the show, is more likely perhaps to look a little bit more like what we're used to seeing for drones and things like that in here?
It's likely to have a larger fraction of the rotor disc covered by blades, which, there are different designs, but generally, even for Earth, you don't typically see for hovering aircraft as large of a fraction of the rotor disc fill up with blades, because it's not the most efficient way from the point of view of power in hover.
That makes sense. Tell me a little bit about latency, because ultimately one of the big challenges has to be you are about as far from the concept of see it as it happens as you could be. So when you talk about flying and piloting Ingenuity, are we talking about programming more than we're talking about joystick flying?
Yeah, definitely not joystick flying. So it's about, as I said, it's sort of about making the big decisions for the helicopter, but then it has to make all the small decisions itself in real time. And so it's about, looking at where do you want to go, what does the terrain look like, what does the weather look like, what kind of, energy budget do you have, trying to anticipate what are issues that the helicopter might encounter flying over that terrain, looking for landing sites, that's a big one, trying to anticipate how well we can navigate, what kind of errors are we looking at, which is very much driven by the terrain that we fly across. And based on all of those things, coming up with a plan of what a flight should look like, including all the parameters, of course, of what's the altitude we fly at, how fast do we fly, and a bunch of smaller knobs that are kind of in the weeds of the flight software that runs on the helicopter, but that controls how the algorithms work that fly the helicopter in real time. And so to do that, you kind of use a combination of good old-fashioned maps taken, based on images from orbit, and computer simulations that allows to test an experiment with different kinds of flights in simulation before making a decision about what we want the flight to look like. And then when you get to that point, then yeah, it's a series of instructions that are, a kind of computer code, a series of instructions to the flight code that lives on the vehicle that describes exactly what we want that flight to look like. And then we send that off, and we just have to wait. And then anything between several hours and a day or 2 or 3 to hear back about how that went.
How long is the delay? What is the latency when you send a message to Perseverance and to Ingenuity?
So the radio signals travel with the speed of light, and so it depends on the relative position of Earth and Mars, how long that takes, and so that varies between something like 5 and 20 minutes on that order, I believe. So we're talking many minutes. Now in reality, we can't communicate with the helicopter nearly that quickly because there are multiple steps here. Once we uplink something, it will generally go to an orbiter and then on to the Perseverance rover, and then at some scheduled time it will be then transmitted to the helicopter, and then it'll go back to the rover, and sort of that whole chain goes in reverse. And a lot of it depends. It's not just the flight, the light time between Earth and Mars. It's driven by operational cadence. When can we talk to the orbiters? When are they overhead and talking to the rover, and so on? And so that's why it always takes at least a few hours in practice, and sometimes much longer than that.
Mm. So we've got a map up here that shows, obviously, as you mentioned, this started as a technology demonstrator and very quickly ended up evolving into exploration. Tell me a little bit about what we're looking at here, and of course we've got Perseverance keeping close to Ingenuity.
White line here is the path that Perseverance was taking, and the yellow line is where we flew with Ingenuity. And so what you really can't see here is Wright Brothers Field in that first area that we flew in, because it's tiny compared to the scale of this map. Because obviously we covered just a tremendous amount of ground compared to what we had originally thought. Each of these legs, each of these flights have their own story associated with them. I can talk a lot about each flight, in the beginning there, for about the first half of the mission, and then somebody else took over for me at that point, and then I can't tell quite as detailed a story about each of those other flights. But some of them were really nerve-wracking. The one that stands out to me more than anything else is flight number 9, where we took a chance and sent the helicopter off on more than 600-meter flight over terrain that was unlike anything that we'd prepared for. But it was kind of our moment to really prove what a helicopter could do, and we managed to do what we planned and get far ahead of the rover on its path, in a position where we can now really use the helicopter as a scout, and it really underscored the potential of this technology. So it's a little hard to point out on this map, but if you look in the at the bottom right here, where that yellow path kind of crosses this thumb in the terrain, that's what I'm talking about, where you can see that the the rover had to go the long way around just because of the kind of terrain there, and with the helicopter we could fly right across.
That's impressive. And just for people to understand, of course, there was a total of 72 flights. And how many were you originally planning?
Up to 5 was, that was as much as it ever going to be. So 72 is just, yeah, it is. It's just way above what we'd imagine.
And you ended up going for over 1,000 days, 1,004 days, with a vehicle designed for what, 14 days?
1 month of operation after we got dropped to the surface. One month was what we had designed for.
That's amazing. What, out of the flights that you did, that you were in charge of, I mean, I guess you know the obvious one might be the first one, but you mentioned that there's some really memorable ones. What were the ones that had you going home at night just, shaking your head at what you'd accomplished?
Well, aside from Flight 1, like I said, Flight 9 is the one that really stands out, because it was a calculated risk. I knew at that point we were doing something that was well outside of the norm of what we designed for, and I knew there was an absolutely a risk that it wouldn't work, but I assessed that the potential benefit here in terms of what we could prove here outweighed the risk, and so that that was why I made that decision. And yeah, it's just obviously then you're nervous, right, about the outcome. I don't know how to say other than that, and just to see it work then, when we came in the morning and we, data started trickling in, and it actually had done what we tried to accomplish. That was just an amazing moment, and I felt like that was when the helicopter really broke through and really showed what it could do. It went from being a technology demonstrator to really being an explorer.
Yeah. What of all the performance things? I mean, obviously you do a lot of analysis afterwards of how it's, its speed, its ability to do altitude, its duration. Out of all the things, what sort of metric there or performance characteristic of Ingenuity really exceeded your expectations the most? What were you looking at and saying, I didn't expect it to be this good?
There are several. The navigation system was a thing that we were quite worried about up front, because the navigation system is based on looking down at the terrain with a camera and then tracking features. So that's how it orients itself. And so we were always worried about, what if we arrive and the terrain is very bland, so there isn't really anything for the helicopter to look at to orient itself. And that's a very valid concern. And it was part of the calculation when we decided to drop it where we did. It was a great area from the point of view of having features to look at for the helicopter. There were other areas nearby that might have been an option, but that didn't score as high on that metric. But then as the mission went along, we challenged it more and more, and it turned out to be very robust. So we flew over some incredibly bland terrain, and the helicopter kept working. So that was, I think, a surprise just how robust that was. I'll say that in the end, that was the thing that caused what happened in Flight 72, where the mission ended as well. So it was a valid concern all along, and it worked, well beyond expectation. But there was a limit to what it could handle with the navigation system.
What about altitude? What was it able to do having to do with altitude?
Yeah, so we flew it at 24 meters. That was the highest we flew, and that was so the biggest limitation there is just the range of the altimeter. So we have an altimeter, which is, it's a laser rangefinder, and not like a standard altimeter. It's a laser rangefinder that uses time of flight to measure the distance to the ground below, and it had a limited range, and so we were quite careful and conservative up front, but we kept pushing that limit as well. So the highest it flew was 24 meters, but in theory it could have flown much higher than that had we had the altimeter to do that.
And what are we looking at on this image?
I need to orient myself on where we are here. Do you remember which flight we're looking at?
I can find a different one here. Let me give you one that's a little more accurate. This actually is something that came off of JPL that shows the kind of how far you actually were able to travel across all those sols.
Yeah. So obviously, you know, Perseverance and Ingenuity, you can compare them in different ways, but it's obviously Ingenuity can go further faster, but it also operated at a much lower cadence than Perseverance, and so there, you know, you see that, you know, how that went, how that played out, and part of the story here too is that during that winter season that I talked about, we didn't fly very much because we didn't have much energy to do that with. So we kind of sat and, you know, did a few intermittent flights over short distances. But Perseverance, of course, was operating as it has been all along.
Got it. And then, of course, you mentioned when it reached the end. Tell me a little bit about that.
Yeah, so you can kind of see it in this image that the terrain where we ended up at the end is extremely bland. So whereas we'd flown Ingenuity into areas that we thought were, you know, really bland already, in flight 70 and beyond, we entered an area that turned out to be even more bland than anything that we'd seen before. It was also combined with fairly high local slopes on these sand ripples in that area. And so what happened is in flight 71, we made an emergency landing driven by the helicopter's lack of ability to track features on the ground. It said, I can't see enough features on the ground. I have to get down to the ground. And so that happened in flight 71. And at that point, you know, when we got the data down from that, we knew that we were in a bit of a tough spot because we had, you know, we were in an area where the navigation system was struggling. And so flight 72 was an attempt to baby step our way out of that, just to do a short flight up and down, you know, similar kind of flight as just flight 1. We just fly up and down, but to get an image of the ground and be able to relocate ourselves globally and see which direction we were facing. Because after that flight 71, we weren't even sure which direction we were turned in. So that was what flight 72, what we were hoping to accomplish, but it's exhibited many of the same symptoms as in flight 71. It had a hard landing, and after that, we asked for some images from the helicopter itself, and it's not the image you see here that was taken by Perseverance, but the image that we got from Ingenuity itself very clearly showed that the tip of the blade, one of the blades, had broken off. And later we found out that that was the case for multiple blades. And you can even see a blade here that's missing entirely, was flung out from the helicopter. So what we believe happened here, there are a couple of potential hypotheses that are valid here, but the one that we believe, you know, that we have the most belief in is that we simply did a hard landing, and then the loads, we didn't contact the ground with the rotor, we're quite confident about that, but that the loads that the rotor saw as a result of that hard landing were simply too much for the structure, and it snapped off at sort of the weak point along the blade span.
Yeah.
And of course, at that point, it was unairworthy, and we realized that right away.
Yeah. But again, to cap that off, that was after flying for a total of 2 hours and 8 minutes, plus over 1,004 days and covering around 11 miles on Mars when it was originally planned to be that 1 month, 5-flight experiment just to show it was possible. That's amazing.
Oh yeah, and so it was a huge success, and the fact that it ended, well, it had to end one way or another, and to me, it ended, pushing further and further until, okay, we reached a point where, we'd pushed it just a little bit too far on one axis, and that was, the navigation axis, flying into this terrain that just was a little bit too much of an ask, and that's okay, right? We were there to push the boundaries. So I think it went out, in the perfect way.
Absolutely. So now you are working on the future and the future of NASA and JPL Mars helicopter program. So tell me what you're up to. What can people expect moving forward?
So we're working now on concepts for future helicopters, technology that we could put to use for future helicopter missions. So there are a couple of things there. The main thing that we've been focused on recently is how can we scale this technology up? Ingenuity proved that it's possible to fly on Mars, but did that at a small scale. And so the question we were asking ourselves is, what if we want to build something large, something that can carry, for example, its own science payload on Mars, on the order of multiple kilograms of payload? What does that helicopter look like? And it became clear pretty quickly that if you want to lift mass on the order that we were trying to do, then you got to go to a different looking helicopter, a helicopter with a different rotor configuration. There are limits to how much you can scale up this particular helicopter. We're just making it larger, and that's just because different kinds of things that matter scale differently. So volume and mass and thrust and power and stiffness and strength, all of those things scale at different rates as you make things larger. And so we have a concept there, and it's not an approved mission. There's no mission baseline for this, but we have a concept that we put out some material on recently that we call Chopper. And this is a beast, right? It's a helicopter that would fill up an entire aeroshell that was used to transport Perseverance to Mars. So we're talking 3.7 meters tip to tip. But this would be a very capable platform that could fly on the order of 3 kilometers per day. That's what we're envisioning for this. So we've done a lot of work on that and feel like we now understand that much better than we did before. And of course, we hope, but the goal of putting a technology demonstration like Ingenuity on Mars it's in a sense it's all about the future, right? You're proving that the technology is up to the job, but it's all about what you can then do with the technology going forward.
Well, it sounds like there's a lot of amazing stuff to come. Do you have any ideas when a program like that is likely to be, if approved, when it would be? Like what time horizon are we looking at, if you're just guessing, for the next time that we get to see a helicopter on Mars?
It's not my role to speculate on that, so I'm not gonna do that. My job is to try to get the technology ready, and so we're doing that. We're studying the problem and getting the technology ready.
That makes a lot of sense. So what would you say the biggest lesson that you guys learned from Ingenuity that you're now applying moving forward?
That's not an easy question to answer. It really depends on what phase of development you look at. There are lessons that were learned while operating it on Mars, but there are also a lot of lessons learned during the development itself. I think one of those lessons is that testing, has to be front and center. That was one of the ways that we did Ingenuity, is we built a lot of hardware. We did a lot of testing. We did, had to invent a lot of ways to test a Mars helicopter on Earth, but it paid us back in that we gained an understanding that we simply would never have had we not gone through that effort.
I think that becomes very evident when you look at this kind of last image I'll show, which, as I understand it, was one of the very, very early just sort of experiments.
Yeah, so this was the first helicopter that we flew in free flight in the Martian atmosphere. And so this picture would have been taken in 2016. That's when we built this helicopter. And it's a full-size Ingenuity rotor. So the blades there look the same as they did on Ingenuity. But the rest of the vehicle obviously doesn't look very much like Ingenuity. It's basically just a mast with a motor on it, and it doesn't have its own batteries. It doesn't have its own solar panel or telecom system, or not even an onboard flight computer. That was all done to, it was tethered. There's a cable hanging below it, attached to equipment on the outside of the chamber. But we used this to do our first demonstration of that it's possible to control flight in Martian atmospheric conditions inside a facility that's called a 25-foot space simulator here at JPL. So it's basically, there's a big vacuum chamber, and we use it for all sorts of missions, but especially for the helicopter, we made incredible use of this as a test facility. And so flying that contraption that you see there was really one of the biggest milestones along the way in the development of Ingenuity.
Well, again, I just want to say thank you so much for joining us tonight on the show. I think that it's really fascinating to those of us who watched the evolution of all of this, to being able to see the size and the scale that this image really shows of vehicles that have made it all the way to operating on Mars, and to the idea that under your leadership of being the pilot of it, that we actually flew for the first time. It is truly, truly amazing. Well, Håvard, thank you so much for joining us here on SocialFlight Live. It's been absolutely fascinating, and we'll be watching that space very closely to see what's next and what comes out in terms of new technology and new missions from NASA and JPL.
Thank you so much. Thank you for having me.
Absolutely. Have a wonderful evening. And to all of you, thank you for taking time out of your evening to join us here on SocialFlight Live. We're off next week doing adventures all over the place, but we'll be back for a very special show, September 30th, Tuesday, September 30th, 8 p.m. Eastern. As always, you do not want to miss this one. It is Hoot Gibson, astronaut Hoot Gibson. We're going to talk about his test piloting, his air racing, building experimental aircraft. He is such absolutely fascinating and amazing individual. He was here on the show not too long ago, and we just barely made it through his astronaut days. And so I can tell you, he is excited. He wants to come back because he told me, he said, Jeff, look, that's all great, but I love racing, and I want to come back and talk about all the things that he did racing. He is so accomplished at that, and I'm telling you, so if you want to see an exciting show, be there Tuesday, September 30th, and then the next week, October 7th, Tuesday, October 7th, we have got some very cool stuff, innovative programs that are being developed to protect general aviation aircraft from drones. This is really, really important stuff, and it's going to affect you and your flying if you're a pilot. So join us there. We're going to be joined by Avionics. Shane Woodson will be joining us there. Great friend of mine, wonderful human being, and he's got a lot to tell about some very, very cool technology coming out that makes all the difference between you having to avoid drones and drones having to avoid you. Key difference there. Join us for that show. Until next time, I'm Jeff Simon for Social Flight, and I wish you all blue skies.